Good day, it's your main chiefs again. We're moving on with electrostatics, the second part. Let's just look quickly on the screen and figure out if we still remember some of these things. Electric fields, do you remember them? Around a positive charge? Yes. Always pointing away from the positive. This is the direction that a positive test charge will take if placed within the field. Alright? Here is an electric field around a negative charge, and it's showing you the direction that the positive test charge would go if placed within the electric field. Alright? Here's an electric field diagram that shows two positively charged bodies, okay, or spheres, alright? 2 point charges that are positively charged. There's going to be repulsion here, while the second one here is showing an attractive force. I think you must remember from your work from previous grades what happens when you got a positive and a negative. The only difference between a positive and a negative is, a negative and a negative is that the negative will have arrows pointing towards the negative. The arrows will change direction. They would look like that. However, the diagram will be still the same, except maybe the negative and negative here. Alright, so I don't have a diagram up here on the repulsion that's showing two negative, but I'm sure you have an idea of how it looks like as you take a look at what I have just presented here. The next part is, how about two ends that are positive and negative. Alright, you can see that they are equidistant from each other, always pointing towards the negative. Only changes around here. Okay, as you can see, it becomes rounder as you get closer to the edges. Alright, I'm sure this gives you a clear picture of how the electric field lines would look like in different situations. This and other pictures of electric fields you can find within our workbook, the workbook Study Guide 1, Revolutionary Science, by Norman Mvotsi and Timothy Siveko. Alright, let's talk about electric field, which I just introduced, and here are some examples of the electric field. Electric field is a region or a space in which an electric charge experiences a force, right? It is a region or a space, okay, in which an electric charge experiences a force. That is an electric field, alright? The direction of the electric field at a point is the direction that a positive test charge would move if placed there. I think I've explained that. There's electric field lines that across each other, they're at right angle to each other, and they're always pointing towards the negative. Alright, I think that's a quick revision of some work that you have done in the previous grades that involves the electric field diagrams. At this point in time, we must be able to know, or something new that we must learn, is an aspect of electric field at a point. Electric field at a point is the electrostatic force experienced per unit positive charge placed at that point. This is examinable. This is important. This is new information at grade 12 level. We are saying the electric field at a point is the electrostatic force experienced per unit positive charge placed at that particular point. Now, if you look at this electric field at a point, it's given the symbol E, alright? E is equal to F over Q, alright? If you remember quite well, the value for F was K Q1 Q2 over R squared. And in this instance, it's being divided by another Q. We can safely bring this equation to say that F E is equal to F over Q, or it's equal to K multiplied by Q that causes the electric field over R squared. Here is another representation of that particular equation. You find this equation at the back of your exam paper each time that you're writing a paper 1 question. And please master them, know what they mean, and how we write out the units. The units are Newton per coulomb. Alright? That is the unit that we use in our calculation when we look for the value of E. Now, having said that, it is imperative for us to start maybe looking at some questions that involving calculations. Alright, now questions that are involving electrostatics often come together, those that involve electric field as well as questions that involve calculating electrostatic force. So you must be ready when you get into an exam to answer such questions. Here is a question, alright, it's taken from November 2018, and the question is asking us to determine the value of Q. What's the story behind that? There are 3 small identical metal spheres, P, S, and T, running ahead of myself, on insulated stands, are initially neutral, okay? They are then charged to carry charges of minus 15 times 10 to the power 19 and Q and plus 2 times 10 to the power negative 9 coulombs. Alright? Not 19 but negative 9, sorry. Respectively as shown in the diagram below. The charged spheres are brought together so that all 3 spheres touch each other at the same time and then they are separated. The charges on each sphere after separation is now minus 3 times 10 to the power negative 9. Now, what happens when you bring charges together? What happens when you bring particles or spheres together? What happens is that they share. The one with more electrons will transfer electrons to the other until there is an equal distribution of electrons. If I have, for example, or in this instance, 3 different spheres and they are coming together, what's happening with those 3 different spheres is the average of their charges is going to be the resultant charge. So the question 7.1 is saying determine the value of Q. We know that once they are separated, the Q net is equivalent to the charge of Q1 plus the charge of Q2 plus the charge of Q3 divided by 3. In other words, their average charge. That's after they come together. If there were 2, it would have been Q1 plus Q2 divided by 2. If there are 4, it will be Q1, Q2, Q3, Q4 divided by 4. We find the average. The question is saying calculate the value of Q that's unknown in this instance. Alright, how are we going to go about it? The Q net is minus 3 times 10 to the power negative 9. Right? That's the net after they've come together and have been separated. We know that one of them is minus 15 times 10 to the power negative 9. The other one we do not know. Okay? So when we're finding the average, okay, we add them as they are, minus 15 times 10 to the power of 9. And, because this one shows it's got lots of electrons, that's why it's negative. Yet the other one, we do not know the charge of. Plus, this one that's positive 2 times 10 to the power negative 9. Alright, all these are divided by 3. Okay, now we have to figure out what's the value of Q. That's a simple equation that we can solve. I like these simple equations that we can easily pull out our calculators and be able to calculate without much difficulty. If you calculate Q, the unknown Q here, it is going to be equal to 4 multiplied by 10 to the power of negative 9 coulombs, because that's a charge. Okay, there we go. So for 7.1, we have determined the value of the unknown charge, which is 4 times 10 to the power of negative 9. Alright, now the next question says draw the electric field curtain associated with the charged sphere S and T after they are separated. So what do we know about S and T? After they are separated, both of them have got a negative charge. And we know that negative charges repel each other. Okay? So I want to see, or I must see, repulsion. Right? Where the arrow is pointing, they are always pointing towards the negative, because that's the direction that a test positive charge rule points. And you can actually add a few more. Make sure they don't cross each other. Alright, they must be straight. I advise you to use a ruler on these ones that are on the sides so that they are straight. Don't cluster them and make them look untidy. Just make sure the examiner realizes what you're doing and what you're representing, just like I am doing right here. Okay. There you go, straight lines. Alright, and that will be the electric field. This one is a bit skewed. Let me show that they are actually getting secular here. That's showing repulsion. Why repulsion? Because S is going to be negative 3 times 10 to the power negative 9 coulombs, and T is going to be negative 3 times 10 to the power of negative 9 coulombs, and they are all negative. Alright, this question goes a little bit further, and then it says, the spheres, each with a new charge of 3 minus 3 times 10 to the power negative 9, are now placed at points on the x-axis and on the y-axis, as shown in the diagram below, with sphere P at origin, right? Then it states Coulomb's law. As I said, questions that are involving electric field and electrostatic force are often brought together, alright, in one question. So once we see those questions, we must get excited because we can be able to answer them. Very simple questions to answer. So let's look at 7.3. Did you know Coulomb's law? You must be able to state it. That states that the magnitude of the electrostatic force between two charges is directly proportional to the product of the charges, or magnitude of the charges, and inversely proportional to the square of the distance between them. Alright, be able to state that, write it out as I'm saying it, remind yourself what it is about, recite it time and time again, write it on a piece of paper, stick it up on your wall, and read it day in, day out. Why? Because for 2 marks, the examiner would want you to state Coulomb's law. Calculate, next question, the magnitude of the net electrostatic force at point P. Now, these are now non-collinear forces that are acting at this instance. How am I going to calculate these non-collinear forces? I'm going to consider my S on P, and I'm going to consider my P on T, the 2 different forces with the 2 different distances between them. Okay, so between this one and that one, and between that one and that one. I'll write it out. My F net squared is equal to F PS squared plus F P T squared. Alright, now for me to find my F PS, I'm going to say K multiplied by Q1 multiplied by Q2 all over R squared. My K is 9 times 10 to the power 9 multiplied by Q1. We know that Q1 is now the same value as Q2, which is 3 times 10 to the power of negative 9. Remember that we don't put in the negative sign. It's repulsive, we already know. Okay, divided by, what is the distance between P and S? The distance between P and S is 0.1 meters. 0.1 meters squared. Once again, it's a call for your calculator to come out, right? And do the calculation for me. The value is, we have done so much practice on this, so it should be easy. 8.1 times 10 to the power of 9 newtons. Okay? That is the answer that we get. 10 to the power of negative 6, newtons. Alright. So that's PS. Now PT, alright, as a result of PTF, PT is going to be equal to, once again, K, QP, QT over R squared, 9 times 10 to the power of 9 times 3 times 10 to the power of negative 9 times 3 times 10 to the power of negative 9, all divided by the distance, which is 0.3 all squared. Once again, another practice for your calculation work is 9 times 10 to the power negative 7. 9 times 10 to the power negative 7 newtons. Okay, right, the relationship between these two, alright, it's a repulsive force, so this is going to work downwards, and also this is going to work in the left. You can choose to put in the direction right there. So this one is going to work downwards on P, although you might not get extra marks for that in this instance because it's in the process of working out. However, it helps us come up with a force diagram that helps us to calculate the resultant. Okay? And this resultant can be found, as we said, by F net squared. So F net squared is equal to 8, 1 times 10 to the power negative 6 all squared plus 9 times 10 to the power negative 7 all squared, and our F net is the square root of that. Alright? Find the square root both sides. That should be a very easy thing to do. If you find the F net as the square root of what you have to the left and the square root of what you have to the right, your answer is going to be 8.15 times 10 to the power of negative 6 newtons. Alright, that will be your answer. 8.15 times 10 to the power negative 6 newtons. That's the net force after you do this particular calculation. Alright, let's move on. Find the net electric field at the origin due to S and T. You would agree with me that we already have a formula that helps us to calculate the F net, okay, the E net. Alright? So electric field is equal to 7.4. E is equal to F over Q. Alright? What is our value of F net? E net over F net. 8.15 times 10 to the power negative 6 divided by, alright, 3 times 10 to the power negative 9. Very simple, right? And that will give us a final answer of 2,72 times 10 to the power 3 is the 10 to the power 3 Newton per coulomb. Alright. You can also go the longer route of finding E net by looking at K multiplied by Q over R squared. You should be coming up with the same answer as I did here, which is 2,7 times 10 to the power 3. Alright? Try it and see if you come up with the same answer. E is equal to K, Q over R squared. Alright? Consider K 9 times 10 to the power of 9 multiplied by 3 times 10 to the power of 3, and then either use 0,1 squared, right? And you would find for that one and for this one, and you'd use also the same calculation of E net on something that is at an angle to find the value of E net. Okay, so you find the E for here and the E for there, and find the value of E net by looking for the square root, okay, of the addition of E1 plus E2, alright? Just like we did on this one, alright? You could follow it through by finding the value of E and use E net squared being equal to E of P and S plus E as a result of S and E as a result of T. You should still come up with the same answer. Alright, the answer is in Newton coulombs. So the next question says, One of the charges P and T experiences a very small increase in mass after it was charged initially. After it was charged initially, one of them experienced an increase in mass. Now, what happens when something has an increase in mass? Let's consider P and T, alright, after it was charged initially. So there's three identical metals, P, S, and Q are initially charged, neutral, okay? So they are then charged. This is the being charged initially, right? When they are charged initially, okay, they are then charged, alright, to carry charges minus 15 times 10 to the power 9 and plus 2 times 10 to the power 9, alright, respectively. Okay, so P is minus 15 times 10 to the power 9, which means that P has gained electrons. The question is, which sphere, P or T, experienced this very small increase in mass? What do you think has happened? What has it gained? It has gained electrons. So therefore, in this instance, we can safely say P gained electrons, or sphere P gained electrons. 7.6, calculate the increase in the mass by the sphere in question 7.61. Let's look for the number of electrons first, and because we know the mass of each electron, we multiply the number of electrons by the mass of each electron. Okay? So what is the mass of an electron? Mass of an electron is 9,11 times 10 to the power negative 31. So let's look for the number of electrons first. Okay, I think we've done a question that looks at the number of electrons. Let this go away and let's try calculating the number of electrons for this particular question. We will leave this part for another question. So let's wipe it off. Disappear. Alright. So if we are saying for 7.6.2, number of electrons is equal to the charge divided by the charge of an electron. Okay? So in this instance, we've got 1,5. Alright, it has increased by 15, up to 15, not 1,5. 15 times 10 to the power of negative 9. That's the charge of the one that is become negative, which is P, that we agreed that it has increased in mass, divided by the charge of one electron, which is 1,6 times 10 to the power of negative 19. That's the charge of an electron, it's negative. If you divide that, this goes away, that goes away. What are we remaining with? We are remaining with to the power negative 9. So 10 of them go away. Doesn't go all of it. It's negative 9, negative 19. So we've got an answer there of 9,38 times 10 to the power 10. 9,38 times 10 to the power 10. Now that's the number of electrons that we have. If we got the number of electrons, to find the mass gained, it's going to be equal to number of electrons times mass of an electron. So 9,38 times mass of an electron, which I said is 9,11 times 10 to the power of negative 31. Our answer is 8,55 times by 10 to the power of negative 20 kilograms. That is the mass gained. Okay, so that's question 7 for us sorted, done and dusted. Let's look at the next one, which is talking about a November 20, I think it's a November 2017 question paper. Yes, A and B are two small spheres separated by a distance of 0,70 meters. Sphere A carries a charge of 1,5 times 10 to the power negative 6 coulombs, and the sphere B carries a charge of 2 times 10 to the power of negative 6 coulombs. All right, the question then says P is a point between spheres A and B and is 0,4 meters from sphere A as shown in the diagram above. 8.1 says define. If a question says define something, it means that we need to have knowledge of it. All right? I remember I emphasized the definition of the electric field at a point, right? Electrostatic force experienced per unit charge, positive charge, placed at that point. All right? So that's the definition that you must have for that particular question as an answer. All right, so it's saying what is the electric field at a point. All right, that's the electric field at a point. Be able to state it, write it in full, and remember it for the sake of examination. It is at a point is being defined as a force per unit positive charge that the charge experiences at that point. Okay, calculate the magnitude of the net electric field at point P. Now you can see that it's linear, okay, collinear, while it's 40 from here, 0,40 from here to there, okay, it is, if you subtract from here to there, you get a value of 0,3, okay, meters. Right? So the question is asking us to calculate the magnitude of the net electric field. Very simple. What we are going to do is consider the E as a result of A and the E as a result of B. And from that end, we must be able to find the total, all right, by adding EA plus EB, all right? So E net is equal to electric field as a result of A plus electric field as a result of B. Now, substitute for EA. is equal to K, or let's just put it in as the net altogether, all right, without further ado. We'll say K, QA, divided by the distance PA plus K, QB, divided by the distance of PB. All right, all squared. Let's do the quick substitution. What do we have? 9 times 10 to the power of 9 multiplied by the value of QA is 1,5 times 10 to the power negative 6, right? And divided by 0,4 all squared plus K, which is 9 times 10 to the power of 9 multiplied by QB, which is 2 times 10 to the power negative 6 over a value of r squared, and our r squared is 0,3 squared. All right, pull out your calculator quickly. Let's do the calculation. And find the answer for this. Okay, and our final answer for that should be 2,84 times 10 to the power 5 newtons per coulomb. Okay, next question 8.3 then says, a point charge of magnitude 3 times 10 to the power 9 is now placed at point P. Calculate the magnitude of the electrostatic force experienced by this charge. All right? So we are looking for the magnitude of electrostatic force. Now what we have is E net. Very simple. Question number 8.3. We know that E is equal to F over Q. For us to find the value of F, we are multiplying E times Q. Do I have a value for E? Yes, 2,84 times 10 to the power of 5. And the Q that has been introduced is 3 times 10 to the power of negative 9. Do the quick calculation and get to the answer. I'm sure it's as easy as cutting butter with a hot knife. This is your man, Chiefs. Ciao.